Hello and welcome to today's class. For today's class, we'll be looking at the solution of the physics practical manual, and we'll be looking at experiment M1. For experiment M1, we have the simple pendulum experiment, and the aim of this experiment is to determine the acceleration due to gravity g from the swing of a pendulum bulb. So the idea is this: we would use the swing of a pendulum bulb to determine the value of g, and g, as we know it, is acceleration due to gravity. Alright, so we have the apparatus and all of this. I'm not going to explain this experiment. I'll just focus more on answering the questions. Alright, so let's look at the table for this experiment. Alright, so we have this table for the experiment. So here's your results. Um, So for this here, you'll be asked to record the time of oscillation, the time for 20 oscillations. All right, the first time, the second, and then you take the mean. Usually for this experiment, you'd have to do T1 and T2 when the length of the thread is 120 cm, 100 cm, 80 cm, 60 cm, 40 cm, and 20 cm. And for each of these, you have to find the value of T1 and T2, all right? So T1 and T2 was got for each of these, and then you have to fill up this other part. Like, you have to fill up this other part. So I'll use this particular manual to explain the whole concept. First things first, you have to fill up the column of the mean. That's here. You have to fill up this column here, all of this. Also, you have to fill up the column for the period, and also you have to fill up the column for T squared. The question is this: how do we fill up the column for each of this? Let's start with the mean. Let's start with mean t. So I'm starting with mean t now. Let's start with mean t. So mean t. Now here's what to note: mean t is equal to t1 plus t2 all divided by 2. Excuse me. All divided by 2. Alright, so this is how we calculate the value of mean t. So we'll take at L equal to 120. At 120, T1 is 45.78. Alright, and T2 is 45.91. So I'll take off this value. It becomes 45.78 plus 45.91. All of this divided by 2. So divide this by 2. So I have this. That's equal to, so I'll punch my calculator to get this value. So if I'm having 45.78 plus 45.91 divided by 2, my answer is about 45.84. That's about 45.84. So this value here should be 45.84. And by the way, when you're filling your table, please make sure you maintain the same number of decimal places. For instance, if you look at this, this was given in 2 decimal places, 2 decimal places, 2 decimal places, 2 decimal places. You'd have to maintain the same 2 decimal places. All right. That means here should rather be 45.84. That should be the value here. All right, do the same thing for all of this. So the second one, that's this. At L equal to 100, this T1 is 41.00, T2 is 40.94. All right, so we'll sum both of them and divide by 2. That becomes 41.00 plus 40.94 divided by 2. So divided by 2. And that's equal to, so let me punch my calculator. I have 41.00 plus 40.94 all over 2. That's about 40.97. 40.97 as the answer. Alright, so this should rather be in two decimal places, not 40.970. Just leave it at 40.97. Alright, so I have this. Next up, let's look at the next one there. Okay, so just to save time, I'll confirm if all of them is correct. So you know what to do, so you can complete the rest. But to save time, I'll just confirm if all of them are correct. Alright, so I've just confirmed that all of these are correct. Just that they are given in three decimal places, which is not supposed to be so. Alright, so please give your answers in two decimal places. So this would now be 36.60. This would now be 32.52. This would now be 25, excuse me. This would now be 25.70, and this would now be 18.17. Alright, so you don't include the zero. So 18.17. So this is how you fill the main T. Alright, just divide the sum of T1 and T2 by 2. So I have that one there. Let's look at the period. So how do we get period? Let's get period. Period T is equal to mean T all over number of oscillations. In this question we have 20 oscillations, 20, as you can see, not just here, but if you go back to, you can see it here, time for 20 oscillation, you can see it here. Not just here, if you go back to the question, let's go back to my question here. Alright, so if you go back to the question, you see, measure the time T for 20 complete oscillations. Alright, so it means that the time that you should measure is for 20 complete oscillations. You can see in this question. Alright, so back to our table. Alright, so we're back here. So let's find the period for each of them. So for the first one, at L equal to 120, that's this one here. For this, I'll divide this by 20. So it becomes 45. First one becomes 45.84 divided by 20. So divide this by 20. Alright, so if I punch my calculator, I have 45.84 over 20. That's about 2.292. That's about 2.292. But don't forget that we have to approximate to two decimal places. That becomes 2.29. So here should rather be 2.29 as your solution. Let's get the next one. So the next one, this would be 40.97 over 20. So 40.97 divided by 20 that's equal to 40.97 over 20. I have 2.05 approximately. That's approximately 2.05 into dp. So this is equal to 2.05 into dp. Next up, I have the next one here. So let me take this one off. Alright, so the next one I have there is 36. That's this one here. I have this one next. That's 36.60 divided by 20. So divide this by 20, and that's equal to 36.60 over 20, 1.83. That's about 1.83 in value. I'm having here as 1.83 in two decimal places. Oh, sorry, 0.83. Okay. So next up, divide this one here by 20. That's 32.52 divided by 20. What do I have? 32.52 over 20. That's about 1.63. 1.63 in value. That's in two decimal places. 1.63. Okay. So what's the next in there? My next task here. Okay, let me take this one off. So next up is this one here. So divide this by 20, it becomes 25.70 all over 20. So 25.70 over 20, that's about 1.29 approximately. I'm having 1.29 in two decimal places. And then finally, the last one here, 18.17. So 18.17, divide this by 20. What do I get? So I have 18.17 over 20. That's about 0.91 approximately in 2dp. So here should be about 0.91. All right. So this is how you fill up the period section. So I think we're done with period now. I'll take it off. All right. So we're done with the period section. Finally, we now have t squared. T squared means I'll be squaring the value of, so this, for to fill this column here, t squared, if you've not done that, is just to square the each of the values of this column here. That's all. So for the first one, I have 2.29. That's this one here. This I will square it. So it becomes 2.29 all squared. Also leave your answer in 2dp. 2.29 squared, that's about 5.24. That's about 5.24 in value. So here becomes 5.24. Okay, so next up, I'm having next one as this one here. That's 2.05. 2.05 all squared. So 2.05 squared, that's about 4.20. That's 4.20 as a value. So here should rather be 4.20. Next up is this one here. So I have 1 point, I have 1.83 all squared. So 1.83 squared, that's about 3.35. I'm having 3.35 in 2dp. This gives you 3.35 in 2dp. Next up, I have this one here. That's 1.63 all squared. 1.63 squared, that's about 2.66. That's 2.66 is your value. So I have here as 2.66. Okay. Next up, I have this one here, 1.29. So I'm having 1.29 all squared. So what do I have? 1.29 squared. That's about 1.66. 1.66 as my value. So I'll have here as 1.66. Finally, I have 0.91 squared. 0.91 squared. That's about 0.83. So I have here as 0. Okay, so let me do that. Let me write it out. 0.91 all squared. That's about 0.83 in two decimal places. So I have 0.83. All right, so this is how we fill up this table. So I'm done with this table filling. All right, so what's next here? So I'm done. So I'm taking this one off. Okay, taking this off. All right, so please let me give you a disclaimer, please. If your values were not exactly this, please do not change your values. All right, use your values the way they are. I am just using this one for illustration. All right, just follow my steps and get your values. Your values must not be like this. All right, so if your value is not like this, please do not change your values. Just use them as they are. All right, so we from the data analysis, we're done with okay, we filled up the table. Let's get to the next thing there, data analysis. That's this. The number one says from the table, plot a graph of L against T squared. A graph of L against T squared. I think the L is small l, so let me use small letter L. A graph of L against T squared. So if I'm plotting a graph, every graph needs a title and a scale. So what would be the title? The title is always easy to get. The title of my graph, since I'm plotting a graph, would be what you're given here. This graph of L against T squared becomes the title of your graph. So that's way easy to get. Alright. So title is graph of L against T squared. Alright, apart from title, every graph must also have what's called a scale. Alright, so we'll plot this graph and then see what our scale is. Alright, so when I plot my graph, I have this. So this is the graph of my work. So go back to the work here. So you ask to plot a graph of L against T squared. For a graph of L against T squared, this L here will be on the vertical axis, also called the y-axis, if you would want to call it that way. And T squared will be on the horizontal axis, that's the x-axis. Alright, so plot L on the vertical axis and T squared on the horizontal axis. And we'll have something that looks like this. You can see L here on the vertical axis. You can see L here. You can see L here on the vertical axis. You can also see T squared here on the horizontal axis. Alright, so you have to note these things. Another thing you have to notice is this. Observe that the value of L, there's an SI unit here, which is cm. Alright, so L in cm. You also have T squared in second squared. So make sure you add the units of the parameters there. So what's my scale here? For this one here, if I look at this from this point, from the origin here to this point, look at this. From the origin to this point, take this off. So I'm saying this, from my origin here to this point here, what I have here is 10. So that means 10, or from, okay, let's call it this way. So for the scale, here is called the origin. From here to this point here is called 1 unit. So that means that 1 unit is equal to, on this L axis, I can see that from here to here, which is 1 unit, is equal to what there? 10. You can see it is 10. So it's equal to 10. 10 watts. This one here is measured, this axis is measured in cm. It's equal to what? 10 cm on the L axis. Alright. Now come over to the T squared axis. My T squared axis is this one here. If I look at this from this point to this point, is also called a unit. So I'll say 1 unit is equal to, if you look at this from here to here is about 0.5. 0.5 is the value. So it becomes 0.5. What's the unit of this part here? The unit is in second squared. That's s to the power minus 2. So that's in second squared. So 0.5 second squared on which of the axis? On the T squared axis. So this is how you write your scale. All right, units, and then put this. So my scale here is, let 1 unit represent 0.5 second squared on the T squared axis. Let me go back and add that. So let 1 unit represent 0.5 second squared on the T squared axis, and and let 1 unit represent 10 cm on the L axis. Okay, and let 1 unit represent 10 cm on the L axis. All right. So with this, I've gotten my title and my scale. Now I can now focus on the graph. So please make sure you always get your title and your scale for each of your graphical work. All right. So back to base. Okay, back to my graph sheet. So I believe I can take this one off now. Okay, so for this one here, the software already helps me to. Okay, so after plotting graph, what's next? It said transform the equation t equal to 2 pi root L over G so that L is the subject of the formula. Let's make L to be subject of the formula. So I can take this off now. Let's make L subject of the formula. So I have that T is equal to 2 pi into root L over G. Let's find L. How do we find L here? Our first task is to square both sides. If I square both sides, it becomes t squared is equal to, since this term is large, I'll put it in brackets. Like since this term here is large, I'll put it in brackets. Becomes in brackets 2 pi root L over G, this all squared. So from here I'll be having t squared. Take off the bracket, it's equal to this square will affect 2. That becomes 4. That's 2 squared gives you 4. Pi will also take each share of the squared. That becomes 4 pi squared. So the squared affects 2 and pi. Again, the square will also affect the square root of L over G. The square will also affect this. So it's more like saying the square affects each of the terms or all terms in this bracket. Alright, so from here, we'll have that t squared is equal to 4 pi squared. From here, square roots would cancel square. I'm left with L all over G. So I'm having this. Alright, so we have to find the value of L. So let's proceed. We're not done yet. From here, I'm having that t squared is equal to, I'm having 4 pi squared times L gives you 4 pi L 4 pi squared L all over G. Alright, so this one here goes to numerator, becomes 4 pi squared L all over G. This becomes all over 1. I'll cross multiply this times this, this times this. So it becomes 1 times 4 pi squared L is equal to G times T squared. So proceeding further, what do we have? Of course, 1 times this is itself. So I'll have that 4 pi squared L is equal to G T squared. To get L, I'll divide here by everything attached to it, which is 4 pi squared. Divide here by 4 pi squared. From here, 4 cancels 4. Pi squared cancels pi squared. So L will be equal to GT, excuse me. So L will be equal to GT squared all over 4 pi squared. So that's the value of L. GT squared over 4 pi squared. Alright. So my answer here is that L is equal to GT squared all over 4 pi squared. Alright, so that's my answer. Alright, the next question here says, number 3 says, hence the slope of the graph of L versus T squared is dash. What's my slope? Alright, going back to my graph. Now the good thing here is that this graph, actually this software I have, actually helps you get the slope. The slope is what you see here, which is about 23.00. So from what I'm seeing here, my slope is about 23.00. Of course, your slope will have a unit, because if I go back to my graph. By the way, if you don't know how to take slope, this is how we take slope. Okay, let's assume my value here was not given. How do I take slope? It's as easy as you come here, you look for the point where, now normally on a graph sheet you have a point like okay, you have a vertical point, you have, excuse me, Normally on the graph sheet you have do I have this in here? Okay, it's not here. Okay, normally on the graph sheet you have okay, let me do that here. Okay, let me use here to illustrate that. mm. All right, let me illustrate it here since I don't have. Okay, let me clean this part too. Okay, so I was trying to say this. Normally on the graph sheet you have lines like this, vertical lines. You also have horizontal lines like this. So to get your point for your slope, all you have to do is very simple. You look for that point that passes through like this, exactly something like this. Yep, passes something like this. All right. So look for that point where these three coincides. That's where you get your. All right. Look for this something like this on your graph sheet, something like this. All right, something like this point here. This is what I'm shading here. Where these three lines, that's one, one, two, and three coincides. So going back to my graph work, this somewhere like let's see, let's assume this didn't give us a slope. So somewhere like this would be good. You can take here like here. Excuse me, that's big. So somewhere like this part here would have been good. So here, also come downwards, look from that point like that. Somewhere like here too would have also been good. So like this, then from like this you can now take here straight like this to this point. Please use your meter rule so it will be straight. From here also come down straight like this. All right, so have something like this. Trace this part here, trace this to this part here. uh that's about 150. Trace this way here, it's about 70. You call this part this is L2. You call this part L1. Trace this down. Okay, also trace this part to down. So you have this. Okay, so this part here would be t squared. Call this t squared 2. Call this part here t squared 1. So how do you find slope? Your slope would be equal to change in L, so change in the parameter of the vertical axis, all over change in the parameter of the horizontal axis, which is what? T squared. And that'll be equal to L2 minus L1 all over this t squared 2 minus t squared 1. So I'll have something like this. Alright, impute values, that will be equal to, so L2, if I trace it this way, I can see that the value is about 150. So it becomes 150 minus, if I trace L1 like this, trace it this way to your left, that's this value here, that's about 70. So minus 70 all over, trace T2 downwards here, that's about this is about 6.5. So 6.5 minus, trace t squared 1 down, that's this, that's about 3. So minus 3, and that's equal to 150 minus 70, that's about 80. It becomes 80 all over 6.5 minus 3, that's about 3.5. So that's equal to, if I do 80 all over 3.5, I have my answers about 22, about 22.86 as my slope. But then this my calculation is not as accurate as what this is giving me. This is giving me 23 as my slope. So I'm taking the value of the software. Okay, if I zoom in from the software, you see that the values, and let me zoom in so you see. If I zoom in from this, you see that these points were not that accurate. I just chose it just to illustrate how it's done. Right? The software has already done a comprehensive and an excellent work, and they gave us 23. So I'll go with 23. But this was just to illustrate how you can get your slope, just in case. All right, so I got 22.86, which is still close to the 23. So hence, I'll say that my slope, the slope of the graph is 23.00, still in two decimal place, Now, something else is that your slope also has a unit. All right, you should know that your slope has a unit. So what's the unit of the slope? The unit of the slope is simply the unit of the parameters being divided. So if I look at this, I had L, or change in L, all over change in T squared. L was in centimeters and T squared was in seconds squared. So then my SI unit becomes cm per second squared. It's that simple, all right? Cm per second squared. So I'll come back to this and add cm slash second squared. This is the value of the slope. All right, next one said the measured value of the slope of the graph, still the same thing. It's approximately 23.00 cm per second squared. All right, so with this, I'm done with this part of the experiment of the of the experiment. Let's look at the next questions, question 5 and the other ones. All right, question 5 says, hence G is equal to, find the value of G, then standard error in G equal to this. So how do you find G? Question 5, how do you find G and the standard error in G? To get the value of G, we simply have to come back to our initial equation. That's the equation that we're given. So what's equation? This one here. This equation where they said T is equal to 2 pi root L over G. Alright, T is equal to 2 pi root L over G. Alright, the equation was, or is, T is equal to 2 pi root L over G. To get the value of G, what we have to do is very simple. We'll first of all make G to be subject to the formula. And of course, just as we did for the first one here, we'll square both sides. So I'll square this. I would also square this. So I'll have that T squared is equal to 2 squared gives you 4. Pi squared gives you, of course, pi squared. For here, the square will cancel the square root. That becomes L over G. I already explained this one before now, so that's why I'm kind of rushing it faster. So T squared will be equal to, this goes to numerator, that becomes 4 pi squared times L all over G. Of course, cross multiply, G times this and then this times this. So it becomes G T squared, that's G times T squared is equal to 1 times 4 pi squared. 4 pi squared L gives you 4 pi squared L. To get G, I'll divide here by T squared, divide here by T squared. So what do we observe? From here, first things first, T squared cancels T squared. So G will be equal to, that's about 4 pi squared L all over T squared. But something looks familiar here. Go back to my graph, observe that I have something that looks like L over T squared. That's this one here. I have something that looks like L over T squared, which was the slope. That means I'll come back here, I'll express this equation in terms of L over T squared. If I express this in terms of L over T squared, what do I get? I'll have that G is equal to 4 pi squared into L all over T squared. This equation is mathematically correct. So the idea is shift out L, shift out T squared, and make them 1 because that's what the slope looks like. But we said L all over T squared is your slope. Alright, look at this. So L over T squared was the slope, the value of the slope, L over T squared. So I'll simply impute that value. What did you get as the value of the slope? Come back to your slope. If you check your slope, alright, so back to this. If you check, the slope of the graph was about 23.00. So I'll put this value back. Alright, it's equal to 23.00. So you can leave the units for now. So G therefore is equal to 4 pi squared. In place of this, I'll put the value of 23.00, which is same as 23. So if I punch this, it becomes 4 times pi squared times 23. That's about, the value is about 4908.00. Okay, and the units of will be, the units will be just L over T squared, which is cm per second squared. So that's the value of the G as gotten from the experiment. All right, so whatever thing your slope gives you, put that value there. That's the idea. All right, 408.00. That's the value of G. All right, so we can say the value of G is about 408.00 cm per second squared. So I have this. Okay. Okay, so how do you calculate the standard error in G? First things first, let's get the percentage error of G. Now, the thing is this, G is a constant, and if you check online, the value of G online is about 980.67 in cm per second squared. So you can just do a quick Google search. The value of G in cm per second squared, you have this value. So how do you find standard error? Now, what we know is this, error is, or a percentage error per se, is equal to error minus exact all over exact. So all over exact. All right, so let's put values there. Now if you look at this value, the one we calculated is actually the error, while the real value, which is this, is the exact. So it should be error minus exact. But in a case where the exact is greater than the error, that's 980 being greater than 908, we'll have to reverse it. That means in the reversal it becomes exact minus error. All right, the reason is because we don't want the value of percentage error to be a negative. So instead it becomes exact minus error. That becomes exact minus error, all divided by exact. So the denominator is always exact. Again, I am stressing that the reason why we are swapping this is because we don't want the value to be negative. The exact is about 980.67 minus the error is 908 divided by the exact. That's about 980 980.67. All right, let's solve this. This is equal to 980.67 divided by 908. That's about 72.67 all over 980.67. 980.67, and that's equal to 72.67 divided by 72.67 divided by 980.67. That's about, this is equal to about 0.07. So I have about just a 0.07 error. Right, for this one here, I won't want to multiply by 100. I don't actually need that percentage value. I only needed this value. So from what I have here, I can see that the value is about 0.07. All right, so how do I write this in terms of standard error? That means my value here, to write this in terms of standard error, it becomes what I have here, 908. So it's equal to 908, you now write plus or minus that value, which is 0.07 in bracket limit SE, standard error, then put the SI unit, cm per second squared. All right. So this is how I express this in the standard error. So this is how we get the standard error. All right. So we have some few questions here before we end this. Questions number 1: explain why the graph fails to pass through the origin. Okay. Number 2: state 2 sources of error and the precautions you took to minimize them. Number 3: it is often recommended that the angle of swing of the pendulum be made as simple as possible. Why? Number 4: what is your opinion? Okay, in your opinion, would the value of G be affected if the size of the bulb is varied? So what if you increase the size of the bulb, the pendulum bulb, maybe make the pendulum bulb bigger or smaller? Would the value of G be affected? Let's answer these questions. All right. Solution to the question. The first one said we should explain why the graph fails to pass through the origin. Let's confirm that the graph does not pass through the origin. All right, so let's confirm that the graph does not pass through the origin. Look at this. Does the graph pass through the origin? From here, you can see that it caused the y-axis, that's the l-axis, at 1.2274. This value here. That means it doesn't pass through the origin. But then let's see if we can zoom in. Let's zoom in. Move this a bit. Uh, Let me take off this calculation so we can see the screen properly. All right, let's try to zoom in. Let's try to zoom in. Zoom in. Excuse me. All right, let's zoom in. So you can look at this. So if I zoom, you can see that this is the origin. Um, this part here is the origin. So observe that the graph does not pass through the origin. It cuts somewhere. It's close to the origin, but it doesn't pass through the origin. So the question now is now saying, explain why this graph does not pass through the origin. That's your question. You have to explain why this graph, look at this, doesn't pass through the origin. All right, so we've zoomed in and we can see that it doesn't pass through the origin. So the question now is explain why this graph does not pass through the origin. Let's go back to our this. Now the answer is this. The reason why the graph does not pass through the origin is due to error. So answer is due to errors in the experiment arising from factors such as air resistance, friction in the pendulum support, and inaccuracies in the length of measurement. That's the reason why the graph fails to pass through the origin. Number 2 says list 2 sources of error and the precautions taken to minimize them. Now the answer is this. Number 1, one of the source of error, or one of the kind of error we can encounter in this experiment, is called random errors. Random errors, example, like error due to what? Parallax. So how do we minimize them? If you look at a table, when we did a table, if you look at the table there, so this in the table we had T1 and T2. What does it tell you? It tells you that we took the time of for 20 oscillation, we took it twice, that's 1 and 2. And the idea was to minimize random error. All right, so we said random errors like errors to parallax. So the precaution we took to minimize the error is that the time of oscillation was taken twice. That was the T1 and T2, and the mean found to reduce the error. All right. So sometimes we take mean just to reduce random errors. That's number 1. The second source is called systematic error from things like air resistance. So when you have the pendulum bulb swinging left and right 20 times, sometimes air resistance can make it to swing slower. All right. So one of the possible sources of error is called systematic error from air resistance. And this, to avoid this, we can say I kept the experiment from drought or air resistance. They asked for 2, but let me give an extra one. The third one is this, that I ensured that the string was vertical before setting the pendulum to motion. So before you tilt the pendulum to start moving left and right, ensure that the pendulum was straight and was vertical, all right, before you start swinging it left and right. So these are like the sources of error and the precaution we've taken to minimize them. The third question there was why the angle of swing of the pendulum must be made as small as possible. So when it comes to simple pendulum experiments, let me try to illustrate this. So let's say I have my retort stand, excuse me. Let's say I have my retort stand, excuse me. Okay, all right. So I have my retort, I have my clamp, all right, and I have my pendulum bob like this somewhere here. Okay, so when it comes to tilting it, you tilt it at a small angle like this, just a very small angle before you release it for so that it could go left like this and come back right like this. All right, so back to the question. The question says, so the question was, why do we make the angle of the swing of the pendulum to be small? Now, why the angle of swing of the pendulum must be made as small as possible? The answer is smaller angles of swing reduces the effect of air resistance, leading to a more accurate result. Also, a small angle of swing will have a more consistent and predictable period. All right, so this is why the angle of swing must be made as small as possible. The final question there is, would the value of G be affected if the size of the bulb is varied? So if I increase or reduce the value of the size of the bulb, would the final answer of G be affected? The answer is no. Why no? The answer is no because acceleration due to gravity G does not depend on the mass or the size of the bulb. So whether you make the bulb to be bigger or smaller, it doesn't change gravity. That's acceleration due to gravity because acceleration due to gravity is a constant. So whether the mass is big or small, it doesn't matter. It would not change the value. All right, so the answer is no. It wouldn't change the value. All right, I think we see. Go back to this. All right, so the last thing there is conclusion. So let's get the conclusion. So what can we say in conclusion? Usually when it comes to doing conclusion, here are some things you should note. So in conclusion, we can say that when it comes to doing conclusion, a proper way of presenting conclusion is to um, first of all list out the aim of the experiment. And I said this experiment was carried out to determine the acceleration due to gravity. So you're kind of reminding them the idea of the experiment of gravity G from the swing of a pendulum bob. Now you now tell them what you did, all right? And I said after taking the time of 20, that should be off 4. After taking the time for, not off, okay, whichever one works. All right, so after taking the time for 20 complete oscillation twice, taking the mean and the period, and also plotting the graph of the length of the thread L to the square of the period, that's t squared, it was found that the acceleration due to gravity is, we got our value as, let's check our value again for G. All right, we got that value again as 108.00. Okay, so acceleration due to gravity is 908 point. So checking back to this, we said that we got G as 908.00. So we'll go back to our conclusion. So it was found that it was okay. It was found that the acceleration due to gravity is, we got 908 is 908.00 cm per second squared. All right, so you can put full stop there. So you can say this was close to the actual value of 980.67 cm per second squared, but a bit different, okay? But a bit different due to some experimental error already stated in the report, all right? Which was these ones we try to minimize, which was the random error, systematic error, and then this one too. All right, so this is the solution to the physics experiment M1. If you enjoyed this video, please make sure you like the video, subscribe to this channel so you can always get content or always get notified when we upload new content. And of course, please share to your friends so that they can also learn. And finally, please leave a comment under this video. Tell us if you understood the video, and also tell us, suggest other experiments you'd love to see. All right, so this is how you can encourage us to create more content like this. Okay, so very simple task. Make sure you like the video, make sure you subscribe to this channel, also share this video to your course mates, to your friends, so they can also learn, and leave a comment. Tell us if you understood the video, and also suggest other physics experiments you'd love to see us carry out. Thank you very much, and see you in the next class.